Let's get started with our today's class. So today we'll be discussing shortest path in graph. Now, before we jump into the topic, let's see what's the motivation behind writing algorithms that can find shortest path in graph. The basic canonical motivation behind this class of problem is definitely everybody likes shortcuts, right? If you have something that you can do faster, if you have something that you can reach in shorter distance, if you have something that you can accomplish sooner, then why would you take the longer route? So shorter route is always preferable in any kind of different problems that you are trying to resolve in your real life. So shortest path in graph, if you can if you can kind of link the real life problem with a graph. So if you can represent that problem in terms of graph, then your problem boils down to just finding the shortest path in this graph. And that's why these algorithms that actually find shortest path in graph, they are widely used. Any interesting motivation that folks here have? Where would you use this shortest path in graph algorithm? It's amazingly quiet. What happened? Are you able to hear me? Are you guys thinking of where would you use shortest path in graph algorithm? Okay, you guys can hear me well. GPS. Yes, in GPS, we can apply it to the distance metrics, where you can say the source and the destination in the graph could be the coordinates of latitude and longitudes from where you want to start to where you want to reach. And then there could be multiple paths. So the distance could be a matrix, and you want to go from your source to destination in the shortest distance. Or time could be the metric where you want to go from source to destination in shortest time. Yes, what else? Databases, Daniel says. Do you mind if you can speak up, Daniel, more on how do you plan to use shortest path in databases? Daniel? Okay, your mic doesn't working, but that's fine. You can type. To connect different databases. Okay, I wish you could explain a bit more. Okay. To connect different databases located in different physical locations and produce faster queries. Okay, that is a bit non-traditional application. If I understand correctly, what you're saying is you're imagining the distributed database scenario where different pieces of data is scattered across various geographical location, and you want to use the shortest path algorithm to query the database faster so that you can get the information from the data centers that are located nearby. And that would, so on that lines, just to expand a bit more, what Daniel might mean, it's my interpretation, is he wants to avoid the network latencies. So if you have data centers that are located farther across on the opposite side of the globe, then definitely everything where you say it's a cloud computing, somewhere that data is physically stored on devices. So if you want to link from one across the world from one corner to the other corner, then you might have to pass through so much network, and network might have traffic, and that's where it might be longer. So what you want to do is preferably you want to query your data or whatever data you want from the database from the locations that are nearby so that you avoid more network traffic. Robotics, Christian says. Yes, robotics is one of very prominent application of shortest path. If you just do a simple Google search online, you should be able to find so many applications on how robotics uses the shortest path. Recently, one interesting one is in Washington, DC, I encountered that they have this cute little automatic robot for delivery of food. And they're just like roaming independently on the street. So they have gone from manual delivery in person to totally automatic delivery. If you order a pizza, the robot comes to your location, it identifies your coordinates, and it stops in front of you. They would message you some code. So if you enter that on the robot, it opens, you can take your pizza, and that's it. So you're done. For such applications, it's a very interesting robotics application. And for such applications, you need shortest path, because when a robot is starting with that pizza from the shop where the pizza was baked to the person whom they want to deliver, definitely you don't want that pizza to be like cold, like as you just removed it from the fridge, right? You want it to be hot and enjoy it. So you want the robot to take the shorter path and reach you faster. Video games is another application. Okay, so I believe now everybody here in this meeting is convinced that yes, shortest path is something that can make our life better, right? In many different aspects. There are interestingly, some of the shortest path algorithms are also prominently used in physics, applying the laws of gravity. It's used in chemistry in accelerating the chemical reactions. So the application of shortest path algorithms is very broad. Now, keeping that in our mind with this strong motivation, let's dive into learning how to actually write a code. That's our job as a programmer, as a computer science people, to write a code that can actually find the shortest path in minimum time. What all did we learn until now? Can someone speak up? The concepts that we learned until now in graph.
We learned what a graph is, the difference between connected and disconnected graph, how to implement a graph in a matrix and linked list format, the different implementations of it, the different uses, like the weighted edges and non-weighted edges, that kind of thing. What integrated,
what else? What else after that? What did we learn after that? After introduction to graph, what did we learn? Come on, you guys are the young brains. We just discussed these in our last week. It's not something that we learned like ages back and you don't remember. I think you guys need a strong coffee. Please get it. Come on. We learned about depth first search and breadth first search, two graph searching algorithms. Now that I said that these are the topics we learned, can somebody please say what are these searches meant to be? What is the goal of these searches? DFS and BFS.
The first search lets you visit every vertex in the graph in like an efficient manner. And breadth first search lets you find the shortest path from like a given vertex to another one. And I guess you can also do the longest path if you like do negative numbers for the weights of the graphs.
Okay, Eris. I would agree that depth first search and breadth first search allows you to find the path in the graph, but I think we need a bit more understanding on whether that's the shortest path or not. I don't think so that DFS and BFS will directly yield you the shortest path, at least in the concepts of our last class that we learned. So the main goal of DFS and BFS is basically to search the graph. You are given this unexplored entity of some edges and some vectors, and your goal is what does exist in this link of edges and vectors, right? So using DFS and BFS, what you do is you explore what vertices are connected with what edges and how does your graph looks basically. So you are exploring from your source until you search all the vertices of that graph, and you parse through all possible edges of that graph. And that's where it's a search algorithm where you can use these both to if you're given some source and some destination, you can use it to search your destination and find the path to reach to that destination. I am assuming that all of you remembers how to define a path at least. So okay, so now that we know that depth first search and breadth first search is used to search something in a graph, we can use them, and we can explore the path from the source to destination. Can we use this DFS and BFS, both of these, to find the shortest path? I need some smart brains over here. You guys are our future of tomorrow. Come on, you have answers to these all interesting questions. Think. So in the problem of shortest path, what we are trying to do basically is how to find shortest path between 2 points. By points, I mean nodes or vertices, something like this in a graph. This is what we are trying to achieve. So a graph, which is definitely conjecture of many vertices and many edges between these vertices, it can be represented something like this, right? As simply as this. So if you have V1, V2, V3 until Vk as your set of vertices, and then you have either directed or indirected edges that connects these vertices. These edges can be weighted. We can call the weight of an edge between V0 and V1 as the W of V0, V1. These weights can belong to any real numbers. It can be fraction, it can be integers, basically any real numbers. And if you have to find the weights of a graph along the path, so basically the shortest path is the path that you can follow that has minimum possible weights. So then we can define the weights of the path as, let's call it the weights of a path, where path is nothing but the combination of multiple edges. That could be said as summation from I equals to 1 to k, because you have k vertices of the weights from v minus 1 to vi minus 1 to vi. right? What would this equation do is it would sum the weights of all the edges that constructs that path P. So the shortest path weight from U to V can be said as let's say U and V are both our vertices. M is just a function. M of U comma V is equal to minimum of WP, where WP is this function which we saw right here. And P is nothing but a path from U to V. I would just represent it with a wavy arrow for ease. It's this if there is a path from U to V. But remember that there are chances that there might not be the path. There might not be a path between U to V, right? Let's say that the problem of shortest path we are solving is the GPS, where we want to go from Miami to FLL. And yes, there would be definitely the shortest path from Miami to FLL. You would be able to find that as soon as you put in the Google Maps by road. But now let's say that I suddenly decide to go from Miami to Bahamas with road. I don't want to take cruise, nor I want to take flight. Then how do you reach? There is no path, right? So there are scenarios where your source and destination might not be linked with the consecutive edges, which we call as path. In that case, the shortest path is nothing but infinity, basically, because infinity represents that there is no roadways that would connect you that would allow you to drive from Miami to Bahamas. And that's why it's infinity. So if there is no path, if there is a path, then we say this is your shortest path mathematically. If there is no path, then let's say it otherwise. So if there is no path, then we say mathematically the shortest path is nothing but infinity. Now for this function is true for any path P that connects U to V with weight WP for this in the graph which we represent with this M function. So this is basically how we would mathematically represent the shortest path. Any questions? Any doubts in terms of what does the weights, path, all these things represent over here? If I don't hear questions, then I do want to hear answers, okay? Keep that in mind. So next, now, while after defining the mathematical formulation of the shortest path problem, the shortest path problem itself can have multiple variants among it. Does anybody want to try guessing these variants? What could be the variants of shortest path problem? With acronym, I'll be just calling SP for the shortest path from now on. Well, the Halloween ghost is not going to haunt you if you answer. So what is the variance of shortest path?
Maybe in the case of like the GPS, it could be the shortest path if you want to do strictly roads, or maybe you can specify if you want to take it like through the highway.
Okay, you are still
So,
thinking on the applications end. Move away from the applications a bit. Let's say that, okay, you figured out an application, you know that the shortest path is something you want to compute. Technically, from the problem standpoint, apart from application, what can be different types of shortest path that you want to find in the graph? Finding path between two vertices. Yes, Ricardo, you are on the correct direction, I would say. So one of the variant could be finding path between two vertices, as Ricardo said, which can also be said as single source, single destination. Now this should click you, definitely. Yeah, that's true. I'm getting answers in the comments. So yes, now these two words clicks you, what can be the other variants, right? So if you have single source, single destination, then you have other variants as just the single source shortest path, where you want to find the shortest path from the source to all other vertices in the graph. So if you, let's say that if we have some graph like this, now if this is your source vertex, you want to find in what manner you can reach all these other vertices A, B, C, D, and find the shortest path to them. The first class of problem is you'll have a single S and a single destination. The second class of problem is you'll have just the source, but you want to find out the destination as each vertices in the graph. The third class of problem is, now definitely most of you might be guessing, the third class of problem is just a single destination. Shortest path. So in single destination shortest path, what you assume is this is a destination you want to reach. But then with assuming the sources to be all different other vertices in this graph, how can you reach this destination in shortest possible way? So these are single destination class of problems. And the fourth and the most cumulative one is all pair shortest path. All pairs shortest path is different from all the above three. It's important to understand that, because in all pairs shortest path, you assume your source to be one node and destination to be all other nodes, but then you also shift your sources. So if your source is this node S, what is the shortest path to all this A, B, C, D? Then you assume that now if your source is this node A, then what will be the shortest path to all the other remaining four vertices? After that, if your source is node B, what will be the shortest path to all the other vertices? So if you have a class of problem where you want to find the shortest path between all the pairs that can be possibly, so given the graph, we can define the graph as the set of vertices, the set of edges, and obviously the set of weights, if it's a weighted graph. So given the graph, if you are if your venture is to find the shortest path between all possible combination of any two vertices, that would be an all pair shortest path. Ricardo has a question. Is this the same as finding the path with fewest edges? Shortest path, it's not always finding the path with the fewest edges. If you're, especially when your graph is weighted graph, as you see over here, this is how you would define your shortest path for a weighted graph. So you can imagine this, you can imagine that here, if you're finding shortest path from A to B, Although the A to B might have a direct edge, but the weight of this edge might be 90, for example. But then there is this another path, you can reach A to D and then D to B, but the weights of this edges might be just 5 and 10. So then your shortest path is not A to B, but your shortest path is A to D to B. So the shortest path need not have always the minimum number of edges, especially for weighted graphs. If it's unweighted graph, will your shortest path will have minimum number of edges? It's a question. If it's an unweighted graph, will your shortest path needs to have minimum number of edges?
Yes.
Yes, because if it's an unweighted graph, basically that's equivalent to assuming that every edge is incurring you a cost of 1, right? So more number of edges, you can imagine it like summing all those ones will give you a cumulative higher number compared to less number of edges. So if this was an unweighted graph where you don't have these 95, 10, all these weights, then definitely A to B, this would be your shortest path in the graph reaching from A to B. What situation would a graph have weights? It's a question from Brian. Well, you say me, what situations, what are the applications in which you would need a graph with weights? I thought you guys would be already understanding this because we already discussed some of the examples. Well, in Google Maps, if you want to reach from the source to destination, you have these all different options, right? Where you can select things like shortest time, shortest distance, constraints like avoid tolls, avoid ferries, all those things. So your shortest time and shortest distance, they are nothing but the weights. Whenever you select the shortest distance, it's the graph between your source and destination is having the weights along its edges, where each edge would represent somehow the presentation of the physical distance in terms of miles. So if number of miles from your this to this vertices is higher, then the edge weight is higher. But if you select the priority of shortest time, then your each edge is somehow the representation of distance, traffic, all those things that would basically increase time, accidents on that road, close downs, constructions, all those things that could increase the time, that represents that edge weight. And basically if you can construct a weighted graph from your actual geographical location to whatever the priority you want to do, then your problem is just finding the shortest path in this weighted graph. Does that clears the application? Okay. Do we have any other questions? Okay, then if there is no other questions, then coming back to the question that I posed in the beginning of this class, this is our problem of finding the shortest path. Can we use DFS and BFS that we already learned to find the shortest path? Yes or no? And you know what? Because it's been extremely quiet in this class, which I don't like, I'm just going to call your names out. If your microphone is not working, you type your answer in the chat, okay? What does the Juan, what do you think? Can we use DFS and BFS to find the shortest path? Juan Rojas. Christian, can I answer? Okay, go ahead. Yes, that's what Christian says. So how many are with Christian? That how many of you think that yes, we can use DFS and BFS to solve the shortest path problem? Basically, if we can do that, then I would say class dismissed, right? Then you guys already know how to find the shortest path. The goal of today's class is achieved.
I think it depends on if it's a weighted graph or unweighted, because I think if you don't have any weights, you can use breadth first search to get it. But if you have weights, you cannot use it. So I think it depends if it's weighted or unweighted.
Okay, so Eris is having some reasons on situations in which we can use DFS and BFS, the situations in which we cannot. Yes, so according to Eris, it's partial. Maybe we can if these constraints are satisfied, we cannot if these constraints are not satisfied. Is there anyone else who thinks that the constraint, who is with Eris?
I think that you can use BFS in the source with the shortest path in the unweighted graph, and BFS and stacked data structures. So I think it's certain conditions.
Okay, Ricardo, I think Ricardo and Eris are on the same point where both of them they're saying that yes, you can use DFS and BFS in some constrained environment, where Ricardo further explained with a particular example that if the graph, you can use BFS for an unweighted graph as to solve the problem of shortest path. Okay, so let's take it case by case, right? What else could be the better approach than taking one of it, taking the hypothesis that we can use it, and then seeing what type of problems will we encounter. So let's say that no problem, Christian, if your mic is not working, you can always type. And everybody, if this is an interactive class, if your mic is not working, at least try to type your comments or be responsive in your comments. This is not a class where you can just put things on, let it play online, and you can do other stuff. Then you won't understand. You need to be with me to understand the contents that we are covering, right? I can lead you until this magical pot of knowledge, water of knowledge, but it's up to you to drink that water. So be with me to drink that water. So let's take at the hypothesis that we are finding the shortest path using DFS. Now, I'm not going to revisit DFS again now, but I assume that all of you have are with me and you have watched all the lectures until now, and you know what DFS is and what DFS algorithm or pseudocode is, what basically it does. So if we are finding shortest path with DFS, then let's take an example that we have this graph where A is connected to B. I'm taking the most complex example where we have weighted directed graph. Our destination is X. But I'm just keeping the graph simple because it's just for our understanding. So let's say this is our graph in which we want to find the shortest path between A and X, these two vertices. And we are using depth first search. So if you're using depth first search, what depth first search will do is we use stack in depth first search, right? So what it will do is it will first push the source, which is A. Then from the source, it will push depending upon, we can say that we are proceeding with the minimum weights as our priority. So then depending upon that minimum weights, it would push B into the stack. This is the stack. And then from B, because we are proceeding in a depth first order, so from B, the only unexplored vertices would be X. It would push X into the stack. From X, the unvisited vertices would be D. It would push that in the stack. And after all this, now there is nothing that could be visited from the D. The D doesn't have any unvisited vertices that we can visit with D as the source. So once this stack is once this is the state of our stack, what do we do next? We start popping things out of stack and mark them visited, if you remember the algorithm. So then we would do that. We would do according to the process of DFS. Basically, while doing this, if you are noting the path on which you reach from A to X, this path you will be getting as A, B, and X as your destination, as your way to reach. Let's say that in this example, because there's only one way to reach from A to X, I don't want that. Let's say we have one more edge with this weight 10. Okay, but still, even with this edge included, this will remain the same, because if the priority is the edges, so among this edge weight of 1, 10, and 2, because 1 is minimum, it will start going in depth in that path of B. So if you are noting the path, it will still give you that this is the path to reach from A to X, which is debatable. It's not true, right? Because if you sum the weights, 15 plus 1, it's 16. If you use this path, if you use the direct path, it's 10. And these are the two ways. So definitely the shortest path from A to X is A to X directly. But then if you are using DFS, what you do is even after you find one path, you modify the original algorithm a bit, and the modifications which you want to do should reflect that you continue your algorithm even though you find a path between source and the destination. So you just take this as one of the option, but after finding this option, you store it. Did anybody say anything? Was there a question? I didn't get it. Can you please repeat it?
I just think someone had their mic unmuted accidentally.
Okay. Okay. So where was I? Yes, continuing the process. So if you modify the original DFS algorithm and have a way to store these paths that you find, as soon as you find a path that connects source to the destination, you store it as option 1, that this is one possible way of reaching from source to destination. But then you don't stop there. Rather than that, you continue your depth first search, and you continue according to the algorithm. So then in this case, according to the algorithm, we would then pop D, mark it as visited, pop X, mark it as visited, pop B, mark it as visited, because these 3 nodes do not have any other unvisited vertices which can be reached from there. But for A, because now we have 2 other options that could be reached from A. So while A is still in the stack, we will next push the second vertex. So because 2 is, if we are having the edge weight as priority, then we will push C into the stack. From C, we can reach D. So these are the things we'll push in the stack. But unfortunately, along this path, you cannot reach to X. So we won't be making a new option or the new path to reach from A to X. Then after this, we will pop D out, we'll pop C out. From A, there is one another option to reach one another outgoing unvisited edge. So with A still in the stack, we will next push X. And while you do that, so while we are making our options, one thing is we are storing the vertices that will allow us to reach from source to destination. And the other thing is you are storing the weights. So if you take this path 1, then you need to, then the weight that it would encounter for this path 1 is 16. Then in this third option, while you finish your depth first search, then you'll have the second option where you will have you can reach from A to X. This will be your second path, the P2, and the weight of this P2 will be 10 because that's the edge weight. And then after completing, so now because there is no other unexplored vertices, you will pop X, pop A, right? And the termination condition of DFS is nothing but when your stack is empty in the algorithm that we saw in our last class. So once the DFS is terminated, then you have all these data that you collect during your DFS to post-process. So you will have this another post-processing function where you will go through each of these options, you will compare the weights of all these paths, and you will pick the minimum. So that's finding the smallest number, or sorting things and then finding the least. If you're sorting in ascending order, then finding the first index of that. In this case, it will be P2. So once you know that the P2 is having smallest weight, and then you return the weight and you return the path of that P2. So A to X, in this case, it's the path. This is an approach in which you need to modify DFS, but by modifying DFS, you will be able to solve the shortest path problem. Now, if everybody understands this approach, any questions on the approach itself? Do we have any speculations on there might be some problem in some particular cases?
Maybe in really large examples with many nodes or vertices, it takes some like an extreme amount of time to go through all the nodes and empty out all the stacks.
Yes, that's not a feasibility problem. That's the operation complexity problem. We'll look into that soon. Brian has a question on the chat. What would be the end case of the algorithm then? It's obvious. The end case will be still what the DFS end case is, which is when all the vertices are visited. In this case, like we ended the algorithm after this, right? After we popped X, we saw that, okay, now there is no other unvisited vertices that you can any further reach. So the end would be the end of this algorithm will be nothing but when your stack is empty. What lets the program know that a path has already been checked if two different paths have some of the same nodes? I'm not sure, Brian. I'm quite getting your question. Okay, but yes, feel free to retype the question in a better way. I'll try to understand it and answer it. Do we have any other questions apart from what Brian is still working on typing in the chat? Okay, so we know that, yes, we can use DFS, and we know how can we use DFS to find the shortest path. Now, the next question is on the lines of practicality. Is this efficient? Is using DFS to find the shortest path efficient? This is what you were saying. Shastri, I think you were saying it.
Yeah, I said like the more nodes and the more vertices, it would take longer to parse through all the stacks. Not parse through all the stacks, but parse through all the options in the stack.
Yes, especially imagine that your graph is having your graph is having a lot of depth into that, okay? And if you visualize this graph that has a lot of depth options and then lot of branches in each depth, what happens is, rather than, because you know that the first choice you take, irrespective of what priority you set, so although we set the priority as the smallest weight, irrespective of our priority, the first choice that we take doesn't leads us to the shortest path. And that's the whole reason you can't end your algorithm as soon as you find any path between the source and the destination. You got to continue and then do all this hectic post-processing. So because we cannot have any better approach at finding the shortest path at our first parse itself, we have to do this work until we are done processing this whole complex graph. And graph could be really big with so many vertices and so many edges. And it's just too much work to get one path. So nope, it is not an efficient, definitely it's not an efficient method, DFS. Next, our question is, okay, now we know that we can use DFS, but it's not efficient. There's one more question in the chat. How would the algorithm work if a path has nodes that have been part of previous checked path? That is, could the problem work if one path is A, B, C, D, E, and the other path is, okay, let me try to draw that. It will make it easy. A, B. Okay, we have this A, B, C, D, E. If one path is this, and the other path is A to D, D to C, C to B, B to E. Yes, the algorithm will work fine, even if so. I think what you are meaning to say is if you have cycles in the graph, that would be the one word terminology, Fran, to say if I understand your question properly. So if you have such type of cycles in the graph, whereas you see that if you're finding the path from A to E, here you have one straight way in which you can reach from here to here, but then there are other ways where you can either go from here to here, or you can go from here to here and then here, right? Because there are these two cycles that you have here in this graph. Let me use another color marker. So you have this one cycle, and then you have this other cycle from B, E, D, and C that connects. So even though if you have cycles, you can definitely use DFS. Now, it's a totally different question. If you assume this is one step ahead, I'm talking, but it's good that you are interested. I'm happy to share the details. If you assume that the cycles have negative weights, then it would be whole lot of other problems. And there are most of the shortest path algorithms, when we use them, we assume that we do not have negative weight cycles, because dealing with negative weight cycles, the problem cannot be mathematically defined, because you keep on, let's say that if you have this simple graph where you have A, B, C, D, just this four, and you have this as your paths to reach from, two paths to reach from A to D, and then you have a cycle where you can go back to the A. Let's say that this edge is negative, which is -5. Irrespective of what all this edge weight is, if you assume it as 1, but still all the time that you keep looping in this path, or you keep looping here, you will be reducing your weight, right? And then that is an ongoing process. How many times you loop in that cycle with the negative weight? So here, this cycle, if you take A, C, and D, that cycle will have 1, will cost you 1 from A to C, will cost you 1 from C to D, but then it will reduce your cost by -5. So basically, it will cost you -3, it's like profit if you take that cycle. So there are some of the examples I like to connect. Let me think of a real life example which says a negative cycle. Let's say you are going on a road where you have tolls, and this tolls does not deduct money from your account, like Easy Pass account, but rather than deducting, it gives you money. So the government wants you to encourage to take this road. And if you take this road, they deposit some money into your account. So if there are some tolls like this, positive and negative, both the tolls, where the tolls can be said as this weights. So you pay one, but then you get $5. Then it doesn't, so finding the shortest path or finding the path that has the most profitable toll will be infinite, because you can basically keep on looping and then you can keep on earning. And that's the reason the shortest path, the class of problems, they do not deal with negative weight cycles. Okay, so this was an interesting diversion. I think it was interesting even for all of you to know about these things, and good we get to these discussions if some of you have some questions. We'll see, that's the benefit of asking questions. It leads to more interesting discussions that can benefit all of you. So coming back to our whatever the task at hand that we took, that using DFS can we solve our shortest path problem. We came to an answer that yes, we can solve if the graph does not have negative weighted cycles. But the problem is it's just very inefficient, because you got to process this whole graph. Graph could be very big just to find the shortest path. After processing the whole graph with DFS, you still need to do some post-processing and too much work to do. Well, shortest path, the whole goal of finding shortest path is to find the shortcut. And if somebody wants to find the shortcut, why would they want to do all this extra work, right? So it doesn't make sense, not efficient. The next thing is, can we use BFS to solve shortest path problem? Now, if you remember, BFS is the class of problem that goes with the breadth. So you can imagine that if A is connected to B, C, and D, we'll explore the breadth of all this, and then we will explore the child node of all this. So first we'll explore A. BFS uses Q. So first we will push A, then we'll push B, C, D, and then we will push, then because A does not have any unvisited adjacent vertex. Okay, what happened? Okay. There we go. It was just one unintentional touch to my pencil. So if A does not have any unvisited adjacent vertices, we remove A from the queue. And after removing A from the queue, we see, we take the element at the hand, which is the head of the queue, and we see if B has any unvisited adjacent vertices. And we keep on pushing and removing the elements in this fourth order. So when you do things like this, now many of you might be on the lines, and also as we just discussed, as Aries and many other, we just discussed before that if we use BFS, then definitely it's a path, it's a kind of way to reach to the shortest path, right? Because you are considering all possible options that goes out, and then you are proceeding on the option. So if these edges had weights, then you are proceeding on the options which has the minimum weight first. So you are inserting things in terms of its weights. In this case, if A to D had weights 2, then we would have inserted D before B. So you are inserting things in terms of their priorities, and then you are processing each of them in that order. So we would have inserted D first because it has minimum weight, and then we will explore all possible options that are going out from the D. If we reach to our destination in the shortest weight, then we'll just mark it out. So if you're using BFS, then we can find the shortest path. Rather, finding the shortest path could be more efficient than DFS, because in case of BFS, you can, as soon as you find the first path from your source to destination, you can say that the first path is your shortest path. You don't have to keep on doing an algorithm like BFS, because it's just the way how BFS processes things. It gives importance to the breadth, it accounts for all possible connections, and then it takes the shortest one and it keeps doing the same in the loop. But, so if we can do this, so now what's the problem with BFS? What are the scenarios in which BFS cannot be used? So BFS can be used to find shortest path if your graph is does not have negative weight cycles, definitely. If your graph, we saw an example, if the graph is undirected, and if the graph is weighted, it doesn't have any problem. Are there any scenarios in which BFS will have a problem?
I mean, yeah, for example, if you're gonna go through one edge to another vertex, that way could be 20, but you could get through the same vertex using like 3 different edges that add to something less than 20.
Yes. Okay. So I think I get what you're trying to say. Let's say if you take weights as the priority. Okay, so for the first time when you parsed the adjacent vertices of A, it was okay. 2 was the priority and you went to the D. Now, if our goal is to find the shortest path from A to this vertex over here, and there are, like, because it's a graph, it's not a tree, they can be the vertices, some vertices like this. So let's say if this is the source and this is your destination, the first path you took was here, and then because this is the shortest one, then you start processing this D vertex in the breadth first order. Then you explored these both. After that, you explore this both, because of breadth first, you will keep on doing it in the breadth first order. There could be the cases where your weights might not be in an ascending order of the path you want to find. So depending upon the distribution of the weights in the graph, this condition that your first path is always the shortest path might not be true. If it's an unweighted graph, perfect, no problem. If it's an unweighted graph, because then each edge will account just for one, and all the edges are considered equally with equal importance, no problem. But if all the edges are not considered with equal importance, that's where BFS might not be able to solve the shortest path problem in the best possible way. Are there any questions in what's the issue with using DFS and BFS to find the shortest path? Okay, so if there are no other questions on this, then I would like you guys to think on, if you want to modify BFS to be able to find the shortest path, how would you play with that algorithm of BFS itself? How would you make it? Is there any way that you can make it to find the shortest path? Though it might not be efficient, doesn't matter. It's inefficient way, but is there some modifications that you can do to the BFS algorithm that will allow you to find shortest path in the weighted graph? Weighted, undirected, and directed, both these types of graph. Think, that's your thinking assignment. Okay, so then because we have 10 more minutes, so what I would like to do is just explain generic shortest path problem. So now that we have understood that with DFS and BFS, the graph search algorithm that we learned, we can solve shortest path problems, but there are some constraints. We can solve only if this conditions are applied. We cannot solve if there are some other conditions. But even if we can solve with these conditions, even if there are some conditions that are satisfied and we can solve the shortest path problem, but still it's just not efficient to solve shortest path problem with BFS and DFS. At least it would not convince me. And I would always think that there might be some another more better way to find shortest path rather than this traditional ways in which I have to do this lot of work and check all these conditions. So we will be learning, next we'll be learning two main graph shortest path finding algorithm. One is Dijkstra's and other is Bellman-Ford. Both these algorithms will help us to find shortest path in a better complexity than what if we find the shortest path by using BFS and DFS. Each of this algorithm have some pros and some cons, some conditions in which one of it is good to use, some conditions in which other one is good to use. We'll be looking at those. We'll be looking at the complexity of how much would it cost us if we use these algorithms to find our shortest path.